So why do we care about composition? Why is it helpful? Where is it useful? Well, I'm going to give you two examples. The first one is called a ripple in the pond. A stone is tossed into a pond and creates an expanding circular ripple. The radius of the circular ripple increases at a rate of 2 centimeters per second. How can we express the area of the ripples as a function of time? So first what we're going to do is look at these two tables. For the values of r of t, that's going to be the radius of our circle after t seconds. And then a of r, which is going to be the area of the ripple with whatever our corresponding radius is. And we are going to leave things in terms of pi as necessary. So remember, our radius is increasing at 2 centimeters per second. So at time 0, before I throw the rock in the pond, my radius is 0. 1 second later, we have increased to 2 centimeters. 2.5 seconds later, we are at 5 centimeters. If I now have a radius of 6 centimeters, that tells me time was 3 seconds. If I have a radius of 19 centimeters, that tells me time was 9.5 seconds. If I'm looking at 22.1 seconds, that means I now have a radius of 44.2 centimeters. So essentially, our radius is double whatever the time is, and our time is half whatever the radius is. So we can go back and forth that way. But if I know time, I can find the radius by taking t and multiplying it by 2. Now let's look at our radius to area relationship. Remember, the area of a circle is r squared pi. So if my radius is 0, well, 0 squared is 0. 0 times pi is 0. After 1 second, when my radius is 1, 1 squared is 1, so I just have 1 pi as my area. If I have an area of 16 pi, that tells me that my radius was 4. If my radius is 6, that means my area is 36 pi. If my area is 5.1536 pi, to find the radius, I need to take the square root of 5.1536, and that is about 2.27. If my radius is 19, my area is going to be 19 squared pi, which is 361 pi. So again, if we know the radius, our area is going to be radius squared times pi. Now that we have this data together, we are going to use the two tables to complete this consolidated table here. So at time 0, our radius was 0 and our area was 0. At time 1, my radius was 2 and my area would be 2 squared times pi, which is 4 pi. At time 2, my radius is 4. We know after 4, when a radius is 4, that we have an area of 16 pi. At time 3, we know that our radius is 6. When my radius is 6, my area is 36 pi. At 9.5 seconds, my radius is 19. And at 19 centimeters radius, my area is 361 pi. Now, here's one that we don't have yet, but if my time is 15, I know that I can double time to get my radius, so that would be 30. Then to get my area, that would be 30 squared pi, or 900 pi. So everything I have done at this point to go from time to area required me to do two calculations. I had to calculate the radius, and then I had to calculate the area. So if we're looking down here, the equation for the length of the radius as a function of time, we already have that. That's our r of t function, 2t, right? We have that here. Write an equation for the area of the ripple as a function of the length of the radius. We already have that as well. A of r, our radius, is r squared times pi. So what if we could now write an equation for the area of the ripple as a function of time? So what that means is I'm going to use composition and plug in r of t in place of r in my area function. So what that will look like is 2t squared pi. I have to distribute the square to both parts here, the 2 and the t. So this becomes 4t squared pi. And what this allows me to do is if I know the time, I can calculate the area without having to first calculate the radius. This is going to save me some calculations. So this column is 4t squared pi. Now, let's confirm that. When my time was 1, 1 times 4 is, 1 squared is 1, 1 times 4 is 4 pi. At time 2, 2 squared is 4, 4 times 4 is 16, so 16 pi. At time 3, 3 squared is 9, 9 times 4 is 36 pi. So what this has allowed me to do is calculate, again, the area of the circular ripple without having to first figure out the radius. It's a direct calculation instead. Okay, one last example. We are going to be carpeting a room. XYZ Flooring has been hired to install carpet in a rectangular room. The shorter dimension of the room is denoted by D and is measured in yards. The longer dimension of the room is 1.5 times as long as the shorter dimension. In addition to a flat service fee of $200, XYZ Flooring charges $3 per square yard of carpeting. Find an algebraic expression of the cost in dollars C of installing carpet in the room. So first we are going to draw a diagram for our rectangular room. And it tells us our shorter dimension was D, and our longer dimension was 1.5 times that length, so 1.5 D. This would be our rectangular room with our given dimensions. Now, what is the area of the room as a function of D? So that means area dependent on D. Well, that's going to be my length times width, which is D times 1.5 D, which gives me 1.5 D squared. Okay. Now, what is the cost in dollars of installing carpeting as a function of the area of the room? So the cost as a function of the area is that $200 flat fee plus $3 per square yard. And we are going to assume that our dimensions are in yards, and it does tell us that up here. It's being measured in yards. So 3 times my area. So what is the cost in dollars C of installing carpet as a function of D? Well, if I knew what D was, I could calculate the area and then use that area to calculate the cost, or I can use composition and create a function for the cost in terms of the dimension D. So what I'm going to do is compose and substitute 1.5 D squared in place of A here. So 200 plus 3 times 1.5 D squared. When I distribute, what that gives me is 200 plus 4.5 D squared. So now, depending on whatever D is, I can calculate the cost of the room in one calculation with one equation. So let's choose a value for D and calculate the cost of installing carpet in the room using our function C. So let's think. I'm going to go with D equals 2. 2 yards is 6 feet. That seems pretty reasonable for a room. So if I were to do D was 2, that means that C of A of 2 would be 200 plus 4.5 times 2 squared. Let me do that calculation really quickly. 2 squared is 4. 4 times 4.5 is 18. So what we are looking at is $218 to carpet that room. Now, how can I be sure that this is generating the correct output? Well, I could go back to my two separate equations and first calculate the area of D being 2, and that would have been 1.5 times 2 squared. 1.5 times 2 squared. 2 squared is 4. 1.5 times 4 is 6. Now that I know the area is 6, I could plug that into my cost function and get 200 plus 3 times 6, which is 200 plus 18, which does generate the same output. However, this was fewer steps, one calculation with one equation. This was more steps, but we did this to show that we did get the same output both ways. And this wraps up our lesson on operations and composition.